friends, in this video we are going to study about sigmatropic rearrangements. What is sigmatropic rearrangement? Take this example. What is happening here? What is happening here? Hydrogen migrates. The hydrogen migrates at carbon number 1 to carbon number 3. Okay, 1, 2, 3. So hydrogen at carbon number 1 migrates to carbon number 3. Okay, so this is called 1,3 hydrogen shift. Here the sigma bond breaks here and it forms a new bond here. The sigma bond at carbon number 1 breaks and carbon number 3 a new sigma bond forms. That is why it is a sigmatropic rearrangement. Sigma bond travels, tropy means travel. It travels from first carbon to third carbon. That is why it is a sigmatropic rearrangement. As a result, hydrogen moves from 1 to 3. So it is called 1,3 hydrogen shift. This carbon number 1 is called migration origin. Because this is a place where the migration takes place. And carbon number 3 is called migration terminus. Because this is a carbon where the migration ends up. Okay, so migration origin is carbon number 1, migration terminus is carbon number 3. Okay, so hydrogen migrates from 1 to 3, so it is 1,3 sigmatropic rearrangement. And let's see this one. Okay, what is it? This is carbon number 1, 2, 3, 4, 5. So hydrogen migrates from carbon number 1 to carbon number 5. Okay, 1 to 5. So this is called 1,5 hydrogen shift. Similarly, here you see carbon number 1 to here carbon number 1, this is carbon number 7. So the hydrogen migrates from carbon number 1 to carbon number 7. Okay, 1 to 7. So this is called 1,7 hydrogen shift. Okay, and let's see these rearrangements. Look at this first one. What is happening? Here bond breaks. Where is the bond breaking? The bond breakage takes place here at this carbon. Give numbering 1, 2, 3. Similarly, that side 1, 2, 3. Okay, so this is called 3,3 sigmatropic rearrangement because here 3 atoms, there 3 atoms. Okay, after the sigma bond breaks, okay, the other side 3 atoms, this side 3 atoms. That is why 3,3 sigmatropic rearrangement, because after traveling 3 atoms this side, 3 atoms that side, it forms a new sigma bond here. Okay, that is why it is 3,3 sigmatropic rearrangement. This reaction is called Claisen rearrangement. Claisen rearrangement, very important. And instead of oxygen, you see this one is vinyl ether, this side allyl ether. Okay, allyl vinyl ether. Remember, allyl vinyl ether. Instead of oxygen, you remove the oxygen, put carbon. Okay, this reaction is called Cope rearrangement. This is also 3,3 sigmatropic rearrangement, Cope rearrangement. And look at this one. Instead of oxygen, you put nitrogen. This reaction is called, this is also 3,3 sigmatropic rearrangement. This reaction is called Aza-Cope rearrangement. Remember all these three reactions, Claisen rearrangement, Cope rearrangement, Azar Cope rearrangement, all are important. Several times have been asked in the PGTRB exams in the past. Okay, 3, 3 sigmatropic rearrangements. Please remember. And please remember that these reactions go through a cyclic transition state, 6-membered cyclic transition state. At present, we don't need. If we study these reactions in this level, this is enough for TRB. Maybe for CSIR, we have to see little more in deep. Okay. At present, this is enough for TRB. Okay. And let's see this one. Bond breaks here. Okay. 1, 2, 3. Right. Give numbering. Here bond breaks, isn't it? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. What is this? What rearrangement? 7, 7 sigmatropic rearrangement. Okay. Now let's study how this hydrogen shifts take place. 1, 3 hydrogen shift, 1, 5, 1, 7 take place. How the orbitals look like. How do these reactions respond to thermal and photochemical conditions? We are going to see this in detail. Okay. So let's begin with this 1, 3. We are going to study hydrogen shift. Let's begin with 1, 3 hydrogen shift. 1, 3 hydrogen shift. First thermally and then photochemically. Thermally means what we should do. What sort of orbitals we should take. Thermally means we need to take HOMO. Photochemical means we need to take LUMO. LUMO in the sense I mean excited HOMO. Excited HOMO and LUMO are not same in terms of electrons. Excited HOMO there is 1 electron, LUMO it is empty. But as far as the lobes are concerned, they are same. So if you remember LUMO, that is enough for excited HOMO, because we are going to see here only the terminal lobes. Okay, the entire orbitals we don't need here. Only the terminal first and last lobes is enough. Okay, so let us take this one. Okay, 1, 3 sigmatropic rearrangements. Okay, this is 1, 3. Okay, this is 1, 3. 1, 3 means, let me rewrite. This is 1, 3. We need to see the number of pairs of pi electrons. Okay, in order to draw HOMO and LUMO, I have uploaded previously some other video on this, but still let me repeat. We need to see the number of pairs of pi electrons. Here 1 pi bond, here 1 sigma bond, both involved, isn't it? So that means 2 bonds. 2 bonds mean 2 pairs of electrons. Each bond for 2 electrons, so overall 4 electrons, 2 pairs. So 2 bond means 2 pairs of electrons. Okay, 2 pairs of electron means how the lobes look like. HOMO, how will it be? LUMO, how will it be? Please remember this formula, this mnemonic. Everyone loves Sneha, old heroine Sridevi. That means even, LUMO, symmetric. Even, LUMO, symmetric. Odd, HOMO, symmetric. You see, even, LUMO, symmetric. Odd, HOMO, symmetric. Even LUMO symmetric means even HOMO unsymmetric. Odd HOMO symmetric means odd LUMO unsymmetric. That you can remember. So if you remember this is enough. Everyone loves Sneha. Even LUMO symmetric. Old heroine Sridevi. Odd HOMO symmetric. That you need to remember. So here in this case, how many pairs of electrons? 2 pairs of electrons I said. 1 from pi bond, 1 from sigma bond. 2 is an even number. So even LUMO symmetric. Everyone loves Sneha. Even LUMO symmetric. So draw the LUMO here first. Here is the LUMO. LUMO symmetric. Okay, this is what I said as symmetric. First lobe and the last lobe, they are symmetric. If we come to HOMO, Even lumosymmetric means even homo unsymmetric. Okay. Now let us take up the hydrogen. Here hydrogen. You see here the orbital is hydrogen s orbital overlap. Suprafacial overlap is possible. Symmetry allowed. Here it is symmetry allowed, but here it is symmetry forbidden. In that case, only anterofacial is symmetry allowed. Anterofacial is symmetry allowed. Now the rule is for hydrogen shift 1,3 thermal photochemical. I'm sorry. Okay, thermal photochemical. Thermal means, okay, here anterofacial. We used homo, so the overlap is anterofacial. So thermal anterofacial. But photochemical suprafacial. Similarly, we come to 1,5. 1,5. This is 1,5. Look at this. 1,5 sigmatropic. So how many pairs of pi electrons? 1, 2, 3. 3 pairs of pi electrons. 3 is an odd number. Odd means old heroine Sridevi. Odd homosymmetric. Odd means homosymmetric. For 1,5 hydrogen shift, odd means homosymmetric. Odd means homosymmetric. Lumo unsymmetric. Homosymmetric means lumo unsymmetric, obviously. So hydrogen, here there is suprafacial allowed, but here suprafacial allowed here, but here symmetry forbidden, so only anterofacial. So the rule is 1,5 hydrogen shift is thermally suprafacial, photochemically anterofacial. Similarly, if I draw 1,7 hydrogen shift, this is anterofacial, thermally anterofacial, photochemically suprafacial. Remember, suprafacial is always allowed, there is no problem. But anterofacial, there is a problem. If the ring is very small, okay, here, if we take up this one, if we take a 1,3 hydrogen shift, 1,3 hydrogen shift means it goes through a 4-membered cyclic transition state. Okay, 4-membered cyclic transition state, 1,3. Similarly, 1,5 if we take, it goes through a 6-membered cyclic transition state. Okay, 6-membered cyclic transition state. It goes through a 6-membered cyclic transition state. So 4-membered, 6-membered, both are small rings. Okay. So anterofacial overlap is not allowed for small rings because it is geometry forbidden. But if we go to 7-membered, 1,7, it goes through an 8-membered cyclic transition state. It is a bigger ring. So the ring can adjust the strain caused by the twisting of the orbital, anterofacial twisting. Okay. So in that case, it is, though it is anterofacial, this is geometry allowed. Okay. So what I can say means, in summary, 1,3, let me rewrite, 1,3, 1,5, 1,7 hydrogen shift. Thermally, 1,3 thermally forbidden because it is anterofacial. Photochemically possible, it is suprafacial. In the same way, 1,5 photochemically forbidden, thermally allowed. Whereas 1,7, it is possible in thermal as well as photochemical means. Okay, so this is the essence of this discussion. Okay, and if we consider the carbon shift, if we look at the carbon shift instead of proton shift, Let us take carbon shift, carbon. One comma 3, carbon shift. Here, as I said, if we draw the same lobes here, okay, earlier I drew, for thermal condition, for photochemical condition. If I draw the HOMO and if I draw the LUMO, HOMO is unsymmetric, I told you earlier. LUMO is symmetric. Carbon, there is a difference in the way it overlaps with the lobes. It differs from the proton hydrogen overlap. Carbon differs. How means carbon has a p orbital, a dumbbell shape. Hydrogen has spherical s orbital. Here carbon has p orbital. So it uses both the lobe, the single lobe. This is the suprafacial overlap. But here, if I draw the carbon here it is symmetry allowed, but here it is not possible, only anterofacial. At that time, what this carbon does means, it is very different. Please carefully watch. Carbon uses both of its lobe. If it is suprafacial, if the orbitals are symmetric, it uses one lobe. If the orbital is unsymmetric, carbon uses both of its lobe. So this way, 1,3 carbon shift is allowed thermally. But hydrogen, it is not like that. Here the thermal, see this? But here, 1,3 thermal hydrogen shift is anterofacial and it is not allowed. But carbon is not like that. Carbon, in the case of carbon, this is possible because carbon uses both of its lobes. So in that case, carbon shift is possible under thermal condition as well as photochemical condition. If the orbitals are symmetric, carbon uses only one of its lobes. If the orbitals are unsymmetric, carbon uses both of its lobes. So in that way, carbon shift is possible under all conditions, thermal condition as well as photo conditions. Okay, but only one difference. If carbon uses only one lobe, the stereochemistry is retention. If we uses both the lobes, stereochemistry is inversion. Look at this reaction. In this reaction, what happens? Carbon, this is given number 1, 2, 3. There is a carbon shift from here to here. Okay, 1, 2, 3. So this is a 1,3 carbon shift. But look at the stereochemistry. Here methyl is front. Here methyl has gone back. That means 1,3 carbon shift. Normally it is, if it is hydrogen shift, it is forbidden, geometry forbidden, thermal condition, geometry forbidden. Here it is possible because it uses both the lobes, and that is why the stereochemistry is inverted. Okay, when the carbon uses both of its lobe, stereochemistry is inverted. But carbon shift is possible thermal condition, photochemical condition, everywhere, unlike the hydrogen shift. Okay, so you understood. So we can predict all these things without using all these formulas, this HOMO, LUMO, everyone loves Sneha, old heroine Sridevi. You don't need anything at all. Simply by using a simple mnemonic, you can find out whether a reaction is possible or impossible, whether it is allowed or not allowed. Okay, that we can predict by using a simple mnemonic. Look at this. It is this one. Yeah. Etka Opka. Okay, Etka Opka. That means E1 thermal, con rotation, anterofacial. Odd photochemical, con rotation, anterofacial. So we don't need this con rotation and all here. We don't need. We can leave it. Remember Etka Opka. Etka Opka. E1 thermal, con rotation, antera. odd photochemical conrotation antera. Okay, even thermal antera means even photo supra. Odd photo antera means odd thermal supra. So this is what you need to remember, ETKA, OPKA. Okay. Now using this simple mnemonic, this is a sense of the Woodward-Hoffman rule. Okay. If you remember this mnemonic, you can predict all these reactions. Let's begin with this one. You see, the first reaction we saw, this 1,3 hydrogen shift. Okay. How many pairs of electrons? Here 1, here 2, here 2. That means overall 4, 2 pairs of electrons. 2 is an even number. Look at the formula. What does it say? ETKA, even thermal antera. That means even photo supra. So we want suprafacial. For small rings, we want suprafacial. So that means this reaction is possible only under photochemical condition. So 1,3 hydrogen shift is not allowed thermally. It is possible only under photochemical condition. That we have already seen with the help of orbitals and all. And let's see this one. This next reaction, where is it? Yeah, and let us see this one, 1,5 proton shift. How many? 1, 2, 3. 3 pairs of pi electron. 3 pairs of electrons. 3 is odd number. Odd photochemical. Look at the formula. Odd photochemical antera. Odd thermal supra. That means this reaction is feasible only under thermal condition. Then only we'll get suprafacial, thermal condition. This we have already seen that it goes through photochemical. And look at the 7 number, 1,7, 1, 2, 3, 4, 4 pairs of electrons. 4 is an even number, even photo supra. Okay, that means this reaction is feasible under photochemical condition. Remember, these two are small rings, goes through a small cyclic transition state. So only suprafacial is allowed. In that case, this is possible only under photochemical condition. Here only under thermal condition. But here it goes through 7-membered cyclic transition state. Since the ring is bigger, supra is allowed, photochemical also allowed. If we use photochemical condition, suprafacial. In case if we use thermal condition, it is antrafacial. Both are possible. Both are possible because the ring is bigger in the transition state. Okay, so and let's see these rings, these reactions. Okay, Claisen rearrangement. How many pairs? 1, 2, 3. 3 pairs. Odd number. Odd thermal suprafacial. That means this reaction is possible under thermal condition. Here also same thing. Okay, thermal. And look at this one. This one, how many? 1, 2, 3, 4. Again, 5, 6, 7. 7 pairs. 7 is an odd number. That means this reaction is feasible under thermal condition. However, this is a bigger ring. Okay, bigger ring. So this is possible photochemical condition as so also. Okay, also since the ring is bigger in the cyclic transition state, it should be a bigger ring. So these reactions are thermally possible. Okay, odd number, odd thermal suprafacial overlap. Okay, so remember ETKA, OPKA. If you remember that, you can predict the reaction whether it is feasible or not under thermal or photochemical. You don't need Sneha, you don't need Sridevi as well. Okay, ETKA, OPKA, please remember. Hope you understand. If you have any queries and comments, please write it in the comment box, and wish you all the best. Thank you very much, and we'll meet in the next video. Thank you very much.